Recall that the temperature of a substance is directly proportional to the degree of molecular activity. As energy is added to a substance, the energy of the molecules increases and the temperature increases. Different substances require different amounts of energy to increase their temperature by a given amount. For example, it takes about 4.5 kilojoules of energy to increase the temperature of 1 kilogram of iron from 20 degrees to 30 degrees Celsius, while it takes about 9 times as much energy to increase the temperature of 1 kilogram of liquid water by the same amount. This means that liquid water can store more energy than iron. We want to define a property which will allow us to compare the energy storage capabilities of different substances. The specific heat of a substance, C, is defined as the energy required to raise the temperature of a unit mass of the substance by 1 degree. There are 2 types of specific heats, depending on how the process is executed. Specific heat at constant volume, CV, is the energy required to raise the temperature of a unit mass of a substance by 1 degree as the volume is maintained constant. And specific heat at constant pressure, Cp, is the energy required to raise the temperature of a unit mass of a substance by 1 degree as the pressure is maintained constant. We will now derive expressions for these specific heats in terms of other thermodynamic properties. We will start with the specific heat at constant volume. Consider a container full of some substance which has some constant volume and mass. Now suppose that we add some differential amount of energy to the substance such that its temperature increases by a differential amount, dt. The principle of conservation of energy on this process states that the differential change of the total energy of the substance is equal to the energy transferred into the system during the process minus the energy transferred out of the system during the process. Remember that our model for the total energy of a system is the sum of its internal energy, its kinetic energy, and its potential energy. For this stationary system, there is no kinetic energy or potential energy, so the total energy of the system is simply equal to the internal energy. There is no energy transferred out of the system during this process. Remember that the definition of the specific heat at constant volume is the energy required to raise the temperature of a unit mass of a substance by 1 degree. So the energy required to raise the temperature of a fixed mass of the substance, m, by a differential amount, dt, is equal to the specific heat times the mass times the change in temperature. Recall that the specific internal energy is equal to the internal energy divided by the mass. Therefore, if we divide both sides of the above equation by the mass, we see that the differential change of the specific internal energy of the substance is equal to the specific heat at constant volume times the differential change in temperature. So the specific heat at constant volume is equal to the derivative of the specific internal energy with respect to the temperature. Notice that this is a partial derivative since the specific internal energy is a function of other properties as well. We will now derive a similar expression for the specific heat at constant pressure. Consider a cylindrical vessel containing a fixed mass of some substance. A piston rests on the substance such that it is at some constant pressure P. Just like in the previous case, we add some differential amount of energy to the substance such that its temperature increases by a differential amount, dt. However, in this case, the substance expands and the volume increases while the pressure remains constant. Therefore, some energy is transferred out of the system as the substance expands and pushes the piston. Just as before, the differential change in the internal energy of the substance is equal to the energy transferred into the system during the process minus the energy transferred out of the system during the process. The energy transferred in is equal to the specific heat at constant pressure times the total mass times the change in temperature. And the energy transferred out is equal to the boundary work done during the expansion process. Remember that a differential amount of boundary work is equal to the pressure times the differential change in the volume of the system during the process. We will now bring the P/dV term to the left side of the equation. Recall that enthalpy is a combination property which consists of the sum of the internal energy and the product of the pressure and volume. So the left side of the equation is equal to the differential change of the enthalpy of the system. The specific enthalpy is equal to the enthalpy divided by the mass. So, if we divide both sides of the equation by the mass of the system, we see that the differential change of the specific enthalpy of the substance is equal to the specific heat at constant pressure times the differential change in temperature. And the specific heat at constant pressure is equal to the derivative of the specific enthalpy with respect to the temperature. The specific heats are properties and therefore depend on the state of the substance. So the specific heats of a substance are functions of pressure and temperature. This means that the amount of energy required to raise the temperature of a substance by 1 degree is different at different temperatures and pressures. Specific heat values of different substances can be found in property tables. Specific heats are properties of a system, and so they are valid for any substance undergoing any process. They are not restricted to constant volume and constant pressure processes. Those processes are simply how the specific heat values are determined. It's also important to note that for a given substance at a given state, the specific heat at constant pressure is always greater than the specific heat at constant volume. This is because, at constant pressure, more energy must be added to account for the energy lost due to boundary work during the expansion process. Let's go back to our comparison between the energy storage capabilities of iron and liquid water. The specific heat at constant pressure for iron at 20 degrees Celsius is about 0.45 kilojoules per kilogram Kelvin, while that of water at the same temperature is about 4.18 kilojoules per kilogram Kelvin. So at that temperature, liquid water has about 9 times the energy storage capacity of iron.